Hello everyone, in this video we'll be looking at section 9.6, which is the ratio and root tests. Both of these tests are tests that we will use to determine whether a series converges or diverges. Subsection 1 is the ratio test, and here we just lay out what the ratio test is. So let the sum from n equals to 0 or n equals to 1, it really doesn't matter whether it starts at 1 or 0 for the ratio test. That's why we don't specify. We just say, hey, this series. So let this be a series with non-zero terms, right? Again, a sub n is just the pieces that we're adding up, right, in the series. So this series converges absolutely when the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is less than 0. The series diverges when the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is either greater than 1 or equal to infinity, which in that case would also be greater than 1. And then finally, if it's exactly equal to 0, if that limit as n goes to infinity of a sub n plus 1 over a sub n is exactly equal to 1, then we can't use the ratio test because the ratio test is inconclusive. So it's called the ratio test because every time we're looking at the ratio of a sub n plus 1 over a sub n. What is a sub n plus 1? That's the next term, right? A sub n is the way the series is presented to you, and you're looking at the ratio of the next term over the previous term, right? So the ratio test is particularly useful for series involving factorials or exponents. So anytime you see a series with factorials or exponents, you should be thinking to do the ratio test. Okay, so let's go ahead and start with an example. The limit as n equals to 0, the sum from n equals to 0 to infinity of 2 to the n over n factorial. Right? So in order to use the ratio test, what am I looking at? I'm looking at the limit. No problem. I'm looking at the limit as n goes to infinity of a sub n plus 1 over a sub n. Right? So let's fill in what a sub n plus 1 is. A sub n plus 1 is this term, right? This is a sub n. It's this term with n plus 1 plugged in instead of just n, right? So a sub n plus 1 looks like 2 to the n plus 1 over top of n plus 1 factorial. And now a sub n is exactly that term, right? So divided by 2 to the n over n factorial. So first thing we notice is the absolute value is redundant because there's no negative terms in this case, right? N is always positive. The only time those absolute values are really necessary is when you have negative 1 to the n or negative 1 to the n plus 1 or something like that. So the absolute values can go away. The other thing that will always happen, and I will, for the rest of this section, always do, is what's going to happen is, notice that I have a fraction divided by a fraction. Right? And how do we typically deal with that? Well, we typically multiply by the reciprocal instead of dividing by a fraction. Right? So this really is 2 to the n plus 1 over n plus 1 factorial times, now we're multiplying by the reciprocal of 2 to the n over n factorial. So in other words, n factorial over 2 to the n. So typically when I go ahead and for the rest of these problems, I won't keep writing this big division problem up here. Right? I'll just realize, and we'll all realize, that when I divide by that fraction, if in this case with the ratio test I divide by a fraction, I multiply by the reciprocal. Okay, so I get to this point, and here's where things will actually cancel out. Right? And so let's do a little bit of side work. So 2 to the n plus 1, I can actually rewrite that as 2 to the n times 2 to the first, or in other words, just 2. Why? Well, remember, when I multiply two things with the same base, what do? I add their exponents, right? So when I multiply 2, when I'm multiplying 2 to the n times 2, I get 2 to the n plus 1, right? So here, let's rewrite this with black. The limit as n goes to infinity of 2 to the n times 2, right, So that's how we rewrite that. Now let's look at n plus 1 factorial. Well, n plus 1 factorial, remember, what does that look like? I multiply every number up to n plus 1, right? And so I do 1 times 2 times 3 times all the way up. What's the number right before n plus 1? N, right? So times n plus 1, right? That would be n factorial. But what do you notice? If I just look at this piece right here, that's the numbers from 1 all the way up to n being multiplied times each other, right? So in other words, every number right here, every number up to n being multiplied to each other is n factorial. So I could rewrite n plus 1 factorial as n factorial times n plus 1, right? And I can always do that. So I'm going to erase this, and then I'm going to move this over because this is a formula that you guys should remember, because this will happen a lot. Remember, because factorials happen as a really good way to use the ratio test, right? So in general, you'll have to do this a lot, where you multiply by the power, or you multiply two things, so you add their powers, and you'll have to deal with factorials. Okay, so then we figured out n plus 1 factorial is n factorial times n plus 1, and then we just leave the n factorial and the 2 to the n alone. So now some things are going to cancel out, right? 2 to the n cancels out with 2 to the n factorial cancels out with n factorial, and I'm left with the limit as n goes to infinity of 2 over n plus 1, right? And now this is just a limit, right? What's the limit? N's going to infinity, so the denominator is getting really big, so this whole thing gets really small. In other words, it goes to 0. So remember, how does the ratio test work? We compare it with 1, right? 0 is in fact less than 1, so what do we know from the ratio test? This series converges absolutely, right? So the question just asked if it converges, so we'll just leave it with converges, but even better, it converges absolutely, right? Okay, so let's look at the next problem here. N squared 2 to the n plus 1 and over 3 to the n. Okay, so what are we looking at for the ratio test? The limit as n goes to infinity of a sub n plus 1 over a sub n. Right? Remember, this is a sub n. So to get a sub n plus 1, I plug n plus 1 into that. So I get n plus 1 squared, 2 to the power of n plus 1 plus 1, or n plus 2 here, all over 3 to the n plus 1. And now, again, we typically would be dividing by a sub n, which is exactly that term, but we'd be dividing by a fraction, so we can instead just multiply by the reciprocal here and multiply by 3 to the n over n squared 2 to the n plus 1, right? Because this right here is 1 over a sub n, right? We're multiplying by the reciprocal. Okay, so remember that this guy right here is really 3 to the n times 3, right? And this guy right here, I guess maybe I could do this in a different color. So this guy right here is really 3 to the n times 3. This guy up here is really 2 to the n plus 1 times 2 to the n. Why did I break it up like that instead of 2 to the n times 2 squared? Well, because I see the 2 to the n minus n plus 1 right there that could cancel out with it. Okay. So let's continue here. So the limit, again, I can get rid of the absolute values because there's no negative 1s in here. And I see that 2 to the n plus 1 cancels out with 2 to the n plus 1. 3 to the n cancels out with 3 to the n. So I'm left with n plus 1 squared times, sorry, this should have been 2 to the first power, right? Because 2 to the n plus 1 times 2 gives me 2 to the n plus 2. So this one should just be times 2, and then I get 3n squared, right? Okay, Well, this is a limit, right? So I can pull out this 2/3 because that's just a constant. And I'm left with the limit times the limit as n goes to infinity of n plus 1 squared. Well, let's go ahead and square out n plus 1. That's n squared plus 2n plus 1 all over n squared. So now I need to evaluate this limit. In order to evaluate this limit, remember I can divide by the highest power of n that happens to appear in the denominator, which is n squared in this case. Right? So I leave my 2/3 alone times the limit as n goes to infinity, and now I take n squared divided by n squared plus 2n divided by n squared plus 1 over n squared, all over top of n squared over n squared. 2/3 times the limit as n goes to infinity. N squared over n squared is just 1. 2n over n squared is 2 over n. 1 over n squared is just 1 over n squared over 1. Now, when I take the limit as n goes to infinity, this guy goes to 0, and this guy goes to 0, so that whole thing goes to 1. That whole limit, right? And so the limit, the total limit with the 2/3 out front is 2/3. And remember, for the ratio test, we compare it to 1, right? In this case, 2/3 is less than 1. So what does that mean by the ratio test? My series, n squared 2 to the n plus 1 over 3 to the n converges, right? It converges absolutely. All right. So now let's look at another one here. So again, we look at the limit as n goes to infinity of a sub n plus 1 over a sub n, right? That's what we look for the ratio test. So the limit as n goes to infinity of, we look at a sub n plus 1. So again, I look at this guy, which is a sub n, and I plug in n plus 1 into where I see an n, right? So this looks like n plus 1 to the power of n plus 1 over top of n plus 1 factorial. And then now I divide by a sub n, which is flipping it over and multiplying, right? So in other words, I get n factorial over n to the n right there. Okay, so what happens? I get, remember that this guy right here is really n factorial times n plus 1, right? So what does that mean? That means these n factorials are going to cancel out. So I'm left with the limit as n goes to infinity of n plus 1 to the n plus 1 all over top of n plus 1 n to the power of n. Okay, so you may be feeling like we're a little bit stuck, but notice n plus 1 appears in both the numerator and the denominator. So I can cancel this factor out with the plus 1 factor there, right? So now I end up getting the limit as n goes to infinity of n plus 1 to the nth power all over n to the nth power. And now we think about rules of exponents. If I'm taking both the numerator and the denominator to the nth power, that means I could rewrite it as the whole thing to the nth power, right? Going backwards. And now what's going on inside of there, again, I can do the thing where I look at, I can, inside of this fraction, I can simplify it. So if I simplify the inside of the fraction, I get n over n plus 1 over n to the nth power. If I simplify this, I end up getting 1 plus 1 over n to the nth power. And maybe you don't recognize that at this point, but hopefully soon you will start recognizing this. This is exactly the definition for e, right? E is that number that's like 2.7 something or another. I'm plugging my calculator really quick. I think it's 2.73. Yeah, 2.72. All right. So this limit, right, by calculus is exactly the limit for E. And so E, remember our final answer here is E. That's a number, right, like pi. And so we're comparing that to 1. 2.73 is in fact greater than 1. So what does that mean by the ratio test? This series from n equals 1, n to the n over n factorial diverges, right? Remember, if it's greater than 1, then it diverges. That was what the ratio test told us. Okay, let's look at the last, and notice here I didn't talk about it, but we lost the absolute values. I can't remember if I talked about that because everything was positive. So in this next example here, notice I have that negative 1 to the n. So here's where that absolute value comes into to do some damage, right? We have, before it seems like every time I'm writing the absolute value of a sub n plus 1 over a sub n, it seems redundant. But in this example, we'll see that it's not redundant because we have that negative 1 there. So since we have the negative 1 to the n, we really do need to get that absolute value to clear everything out. Okay, so a sub n plus 1, remember we look here, this is a sub n, and we plug in n plus 1. So I get negative 1 to the n plus 1. We can go ahead and throw that up in the numerator over n plus 1 n plus 1 underneath the radical, and then n plus 1 is n plus 2. Right? So remember that negative 1 to the n is really up in the numerator because we're multiplying it. So it would go in the denominator here. So I get negative 1 to the n, and then I would get radical n here, and then I would get n plus 1 in the numerator. So again, these absolute value signs say that I am taking the absolute value. So in other words, these negative 1 to the n's get canceled out by that absolute value. Right? We don't have to worry about the negative part. So really what we end up getting is the limit as n goes to infinity of radical n plus 1 times n plus 1 over top of, I'm going to rewrite this as radical n over n plus 2 just because I want to take into account that we're going to combine those radicals, right? So using a little bit of algebra, remember if I have, write it in a different color here, if I have the square root of a over b, that's equivalent to the square root of a over the square root of b, right? So that's what I'm going to do with those radicals, right? Just because they're being multiplied times n plus 1 over n plus 2 doesn't matter. The rules still apply. So I can rewrite this as the square root of n plus 1 over n, and then times n plus 1 over n plus 2. Okay, and now I have to remember the rules of limits. The rules of limits say that the limit can get distributed multiplication-wise, right? So in other words, this is equal to the limit as n goes to infinity of the square root of n plus 1 over n times the limit as n goes to infinity of n plus 1 over n plus 2. Okay, so how do I figure out these limits? Maybe you're good at doing this by now, but let's practice a little bit more, right? Let's go through all the steps. So inside of this factorial, I can rewrite everything, or I can rewrite it with the denominator over n, right? So in other words, I can rewrite this as n over n plus 1 over n, right? And then here, I have both n is happening in the numerator and the denominator, so I do that thing where I divide by the highest power of the numerator that's, the highest power of n that appears in both the numerator and the denominator, which is n. So in this case, it would look like n over n plus 1 over n over top of n over n plus 2 over n. So simplifying everything, I get the limit as n goes to infinity of 1 plus 1 over n times the limit as n goes to infinity of 1 plus 1 over n, 1 plus 2 over n, right? And then again, rules of limits say I can bring that limit inside and I can bring that limit to each term, right? So when I do that, 1 over n is 0, so I get 1 plus 0 when I do that limit inside of there, because the limit of 1 is 1. And then here I get this goes to 0 and this goes to 0, right? So I end up getting times 1 plus 0 over 1 plus 0. I'm writing out all these steps here just to be very careful that you're following. So I get radical 1 times 1 over 1, but all of that is just a bunch of 1s, right? So my limit is equal to 1. Remember what happens in the ratio test when the limit exactly equals to 1? It means that the ratio test is inconclusive, right? So here we can't use the ratio test. So the ratio test is inconclusive. We have to look at some other way to figure out this limit. Okay, and we'll end this video here.